Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. A quiet revolution began in a Swiss patent office. The year was 1905, and the revolutionary, a 26-year-old technical expert, third class, named Albert Einstein, was outwardly an unlikely candidate to reshape the cosmos. His daily work involved the meticulous, often mundane, assessment of electromagnetic devices. Yet, in the interstices of this formal employment, his mind was engaged in a profound re-evaluation of the physical world, wrestling with the deepest inconsistencies that haunted late 19th century physics. From this crucible of thought, in a single year, emerged 4 papers that would forever alter our understanding of light, matter, time, and space. This period, his Annus Mirabilis, or miracle year, represents one of the most spectacular intellectual flowerings in scientific history. The first of these monumental contributions addressed a stubborn and illuminating puzzle concerning the very nature of light. The problem was known as the photoelectric effect. For decades, James Clerk Maxwell's theory of electromagnetism had stood as a pillar of classical physics, a beautiful and comprehensive framework describing light as a continuous wave of oscillating electric and magnetic fields. This wave theory was enormously successful, explaining phenomena like reflection, refraction, and interference with mathematical elegance. Experiments at the turn of the century, however, produced results that were entirely at odds with this picture. When light, particularly ultraviolet light, struck a metal surface, it could dislodge electrons. According to wave theory, a more intense, or brighter, light beam carried more energy and should therefore eject electrons with greater kinetic energy. Similarly, a faint light should require a period of time to accumulate enough energy to liberate an electron. The experimental reality was quite different. The energy of the ejected electrons depended exclusively on the frequency, or color, of the light. A dim blue light would eject electrons with more energy than an intensely bright red light. Furthermore, the ejection of electrons was instantaneous with no discernible time lag, regardless of the light's intensity. These observations presented a direct contradiction to the classical wave model. Physics was faced with an anomaly that its most successful theory of light was powerless to explain. Einstein's solution, presented in his paper On a Heuristic Point of View Concerning the Production and Transformation of Light, was both breathtakingly simple and profoundly radical. He took a concept introduced a few years earlier by Max Planck as a mathematical contrivance to solve the black-body radiation problem and proposed it as a physical reality. Einstein suggested that the energy in a beam of light is concentrated in discrete, particle-like packets, which he called light quanta. We now call them photons. The energy of each individual quantum, he postulated, was directly proportional to the frequency of the light. The relationship is expressed in the famous equation E equals h times f, where E is the energy, f is the frequency, and h is Planck's constant, the fundamental value Planck had derived. This model elegantly resolved the photoelectric mystery. An electron is ejected when it absorbs a single light quantum. The energy of that ejected electron is the energy of the photon it absorbed, minus the energy required to escape the metal surface. Since photon energy is determined by frequency, the electron's energy is likewise determined by frequency. A higher intensity light beam contains more photons, leading to the ejection of more electrons, but the energy of each individual electron remains unchanged unless the light's frequency changes. This explained the experimental data with perfect clarity. The idea of light as a stream of particles was, of course, an ancient one, associated with Newton. Einstein's genius was in resurrecting it within a new quantized framework, creating a synthesis that established the dual wave-particle nature of light, a foundational paradox of the quantum world that physicists still grapple with today. This insight laid the groundwork for quantum mechanics and its technological descendants, from solar panels converting sunlight into electricity to the charge-coupled devices in digital cameras that capture images one photon at a time. Having reimagined the nature of energy and light, Einstein's miraculous year continued with an inquiry into the very existence of matter's smallest constituents. While the photoelectric paper delved into the quantum realm, another of his 1905 works provided the most compelling evidence to date for the atomic theory of matter. The concept of atoms was ancient, but at the dawn of the 20th century, it remained a hypothesis for many influential scientists. They viewed atoms as useful theoretical constructs for chemistry and thermodynamics, while questioning their physical reality. The problem was finding a way to observe their effects directly. The clue lay in a curious phenomenon first documented in the 1820s by the botanist Robert Brown. While observing pollen grains suspended in water under a microscope, Brown noticed they were in a state of perpetual, agitated, and random motion. This jittery dance, which came to be known as Brownian motion, defied any simple explanation. The particles were too large to be moved by minor currents or temperature gradients in a simple way, and the motion never ceased. Einstein, in his paper on the motion of small particles suspended in a stationary liquid required by the molecular kinetic theory of heat, provided the definitive theoretical explanation. He reasoned that the visible pollen grains were being constantly bombarded by the much smaller, invisible molecules of the surrounding water. While the bombardment came from all sides, at any given instant, the number of molecular collisions on one side of the grain would be slightly different from the number on the opposite side. This momentary imbalance would produce a tiny net force, nudging the particle in a random direction. The next instant, a new random imbalance would push it in another direction. The cumulative effect of these countless tiny pushes was the erratic, zigzag path observed under the microscope. His contribution was a masterful application of statistical mechanics. He derived a specific testable mathematical formula that connected the microscopic world to the macroscopic. The equation related the average distance a suspended particle travels in a given time to quantities that could be measured in a laboratory: the temperature of the fluid, its viscosity, and the size of the particle itself. Crucially, the formula also involved Avogadro's number, the number of atoms or molecules in 1 mole of a substance. This meant that by carefully observing the motion of the suspended particles, one could work backward and calculate a value for the size and number of the unseen molecules causing the motion. It transformed Brownian motion from a scientific curiosity into a powerful quantitative tool. Within a few years, the experimental work of Jane Perrin confirmed Einstein's predictions with remarkable accuracy, providing irrefutable proof of the existence of atoms and silencing the remaining skeptics. It was a triumph of pure thought, demonstrating that the atomic hypothesis was an indispensable feature of physical reality. These two papers alone would have secured a place for their author in the pantheon of physics, one establishing the reality of light quanta, the other confirming the reality of atoms. Yet they were merely the prelude to an even greater upheaval, one that would redefine the very fabric of existence. The intellectual ferment of 1905, having already overturned classical assumptions about light and matter, was about to witness its most profound convulsion. The two earlier papers, monumental in their own right, addressed specific, albeit fundamental, puzzles within physics. The work that followed addressed a schism that threatened the entire foundation of the science. Physics at the turn of the 20th century was a house divided against itself, ruled by two seemingly perfect, yet utterly incompatible, monarchs. On one throne sat Isaac Newton, whose laws of motion and gravity described a clockwork universe of absolute space and absolute time, a rigid, unchanging stage upon which all physical drama unfolded. His mechanics worked with breathtaking precision, predicting the orbits of planets and the fall of an apple with equal aplomb. On the other throne sat James Clerk Maxwell, whose elegant set of equations unified electricity, magnetism and light into a single, coherent theory of electromagnetism. Maxwell's theory was an equivalent triumph of 19th-century thought, and from it emerged a startling prediction: the speed of light in a vacuum, a constant designated as c, was absolute. It would be measured as the same value by any observer, irrespective of their own motion. Here lay the crisis. According to Newton's world, velocities were simple to add. If you are on a train moving at 100 kilometers per hour and you throw a ball forward at 20 kilometers per hour, an observer on the ground sees the ball traveling at 120. Common sense dictates this. Maxwell's equations, however, insisted that if you were on a spaceship traveling at half the speed of light and you shone a torch forward, both you and a stationary observer would measure the light from that torch moving at the exact same speed. This was a paradox of the highest order. It violated every intuition about relative motion. To reconcile this, physicists had postulated the existence of a luminiferous aether, a tenuous, invisible medium filling all of space, through which light waves propagated. This aether would serve as the absolute reference frame against which light's speed was constant. Yet the famous Michelson-Morley experiment of 1887, an ingenious attempt to detect Earth's motion through this very aether, had returned a stunning null result. The aether, it appeared, was undetectable, perhaps even chimerical. Physics was at an impasse, armed with two supremely successful theories that could exist together. Into this intellectual breach stepped the patent clerk from Bern. In his paper, On the Electrodynamics of Moving Bodies, Einstein performed one of the most audacious acts in the history of science. He took the paradox by the horns and declared that both Maxwell and a modified version of Newton's relativity principle were correct. He began with two simple, almost deceptively simple, postulates. First, the laws of physics are the same for all observers in uniform, non-accelerated motion. This is the principle of relativity. Second, the speed of light in a vacuum is the same for all such observers. This is the principle of the constancy of the speed of light. The consequences that flowed from accepting these two postulates were earth-shattering, for they required the complete abandonment of a concept humanity had held as sacred and self-evident for millennia, the idea of absolute, universal time. The casualty of Einstein's reasoning was simultaneity. He demonstrated through a powerful thought experiment that two events which appear to happen at the same time for one observer could appear to happen at different times for another observer in relative motion. Imagine a long train moving at a constant, high velocity. A person standing on the embankment precisely midway between two trees sees lightning strike both trees at the exact same instant. For this observer, the two events are simultaneous. Now consider a passenger seated in the exact middle of the moving train. As the light from the two strikes travels towards her, she is moving towards the light pulse from the front of the train and away from the light pulse from the rear. Consequently, the light from the front strike reaches her eyes a fraction of a second before the light from the rear strike. For her, the lightning struck the front of the train first. Who is right? Einstein's profound insight was that both observers are correct, within their own frame of reference. There is no absolute universal now that everyone in the universe can agree upon. Time itself is relative. Once the absolutism of time is relinquished, other classical certainties begin to crumble. To keep the speed of light constant for everyone, space and time must become flexible, dynamic quantities. An observer watching a clock move at high speed relative to them will see its second hand tick more slowly than their own. This effect, known as time dilation, means that moving clocks run slow. Similarly, an observer will measure a fast-moving object to be shorter in its direction of motion than it would be at rest. This is length contraction. These are consequences derived from the mathematical framework known as the Lorentz transformations, which Hendrik Lorentz had developed earlier to explain the Michelson-Morley result. Einstein, however, derived them from his two fundamental principles, revealing them as inherent properties of space and time itself. A few months later, as if this revolution were incomplete, Einstein published a short 3-page addendum. Its title was a question: does the inertia of a body depend upon its energy content? The paper contained the derivation of the most famous equation in all of science, E equals mc squared. This was the final, breathtaking consequence of his theory. It established a deep and fundamental equivalence between mass and energy. Mass, the property of matter that gives it inertia, could be understood as a tremendously concentrated form of energy. The equation reveals that a tiny amount of mass, if converted, can release a prodigious amount of energy, because the conversion factor c squared, the speed of light squared, is an immense number. This principle explained the power source of stars, and decades later would unlock the terrible and awesome power of the atom. It redefined our understanding of matter, showing it was a vast reservoir of dormant energy. The special theory of relativity, as it came to be known, was a complete and self-consistent worldview. It unified mechanics and electromagnetism, resolving the central crisis of 19th-century physics by forging a new, deeper synthesis. It was special because it dealt exclusively with the special case of uniform motion. It left a giant of physics still standing outside its framework: gravity. Newton's law of universal gravitation described an instantaneous force, an action at a distance that propagated across the cosmos with infinite speed. This was now in direct violation of Einstein's new cosmic speed limit, the speed of light. The beautiful edifice he had constructed in 1905 was incomplete. It had no room for acceleration, and therefore no room for gravity. Reconciling his new principles of relativity with the ancient force that holds the universe together would become the defining quest of the next decade of his life, a solitary intellectual struggle that would demand an even greater leap into the conceptual unknown. That formidable intellectual ascent into the unknown began with a moment of startling clarity. In 1907, while still working at the patent office in Bern, a thought came to him, one he would later call his happiest. Imagine, he mused, a physicist inside a sealed chamber, perhaps an elevator, in the deep void of space, far from any gravitational influence. If this chamber were pulled upward by a rope with a constant acceleration, the physicist inside would feel a force pulling him to the floor. If he dropped an object, it would fall to the floor with an accelerating velocity. Every experiment he could perform would yield results identical to those experienced in a stationary room on Earth. He would be unable to distinguish the effects of uniform acceleration from the effects of a uniform gravitational field. This was the principle of equivalence, the conceptual seed from which an entire new cosmology would grow. The implication was earth-shattering. If gravity and acceleration were experientially indistinguishable, perhaps they were, at a fundamental level, the same thing. This insight provided the crucial bridge between the special case of uniform motion and the general case of accelerated motion. It meant that a theory of gravity would simultaneously be a theory of arbitrary motion. Gravity ceased to be a mysterious force acting across empty space. It became an intrinsic property of the reference frame itself, a feature woven into the very fabric of reality. With this principle, Einstein had found his path forward, though the terrain ahead was far more treacherous than he could have imagined. To transform this beautiful physical intuition into a rigorous mathematical theory required a complete overhaul of the language of physics. Euclidean geometry, the familiar world of flat planes and straight lines that had underpinned science for millennia, was inadequate for the task. A universe where gravity was equivalent to acceleration was a universe that must be curved. Light, which travels in the straightest possible line, a geodesic, would have its path bent by a massive object, because the spacetime through which it traveled was itself warped. To describe such a world, Einstein needed the mathematics of curved surfaces and higher dimensional spaces, a field known as differential geometry. Here, the physicist found himself at the limits of his mathematical prowess. His great fortune was a friendship with Marcel Grossmann, a former classmate and a brilliant mathematician. In 1912, Einstein took a professorship in Zurich, rejoining Grossmann. Desperate, he laid out his physical problem. He needed a mathematical framework where the laws of physics would look the same for any observer, regardless of their state of motion, in a universe whose geometry was dynamic. Grossmann identified the exact tool required: the tensor calculus developed by Italian mathematicians Gregorio Ricci Curbastro and his student Tullio Levi Civita. This was the language needed to describe quantities and relationships in a generalized, coordinate-independent way, perfectly suited for a curved, dynamic spacetime. What followed was an arduous intellectual collaboration, a period of intense struggle chronicled in the pages of their Zurich notebook. This artifact reveals the raw process of discovery. It is filled with complex tensor equations, calculations, explorations of different mathematical avenues, and telling corrections. They formulated a preliminary version of the theory, the Entwurf or draft theory, which contained a crucial flaw. For nearly 3 years, Einstein wrestled with these equations, convinced he was close, yet tormented by inconsistencies. He pursued paths that led to dead ends, made mathematical errors that took months to uncover, and felt the immense strain of this solitary pursuit. The quest was to find the precise field equations that would relate the curvature of space-time to the distribution of mass and energy within it. Finally, in a frantic burst of creative energy in November of 1915, culminating in a series of 4 lectures to the Prussian Academy of Sciences in Berlin, he found the answer. He corrected the final error in his previous attempts and presented the definitive form of his theory. The result was a set of equations of breathtaking elegance and power, the Einstein field equations. In their compact tensor form, they are written as g sub mol no equals 8 pi g over c to the 4th power multiplied by t sub mol no. The meaning of this expression is among the most profound in all of science. On the left side, the Einstein tensor, g sub mol no, describes the geometry of space-time. It is a sophisticated mathematical object that encodes information about the curvature at every point in the universe. On the right side, the stress-energy tensor, T sub mol no, describes the distribution of matter and energy. The equation forges a dynamic link between them. As the physicist John Archibald Wheeler would later summarize it so poetically, space-time tells matter how to move, matter tells space-time how to curve. This was Newton's universe turned inside out. Gravity was the curvature of the cosmos. Planets orbit the sun because they are following the straightest possible path through a space-time that has been warped by the sun's immense mass. A theory of such radical scope required immediate verifiable predictions. General relativity offered several. First, it accounted perfectly for a small, nagging anomaly in the orbit of Mercury. For decades, astronomers had observed that the planet's elliptical orbit slowly rotates, or precesses, at a rate that Newtonian physics could almost explain. Einstein's equations, when applied to the problem, predicted the anomalous precession with stunning precision, explaining the discrepancy down to the last arcsecond. The theory's most dramatic prediction was that light itself should be bent by gravity. An opportunity to test this arose during the total solar eclipse of May 29, 1919. The English astronomer Arthur Eddington led expeditions to Brazil and the island of Principe to photograph the stars appearing near the Sun during the eclipse. With the Sun's light blocked, they could measure the apparent positions of these stars and compare them to their known positions months earlier. If Einstein was right, the light from these distant stars would be deflected as it passed through the warped spacetime around the Sun, causing their apparent positions to shift. When Eddington's measurements were analyzed, they confirmed the prediction. The announcement of these results catapulted Einstein from a celebrated physicist to a global icon, the embodiment of scientific genius who had redrawn the map of the cosmos. A century later, general relativity forms the bedrock of modern cosmology. Its predictions, once esoteric, are now part of our daily technological lives. The Global Positioning System, or GPS, in our phones and cars relies on its principles. The atomic clocks on GPS satellites tick at slightly different rates than clocks on Earth, due to effects from both special and general relativity. Without constant correction for this time dilation, the system's navigational data would accumulate errors of several kilometers each day. Furthermore, the theory predicted ripples in the fabric of spacetime itself, gravitational waves produced by cataclysmic cosmic events. In 2015, the LIGO Observatory made the first direct detection of these waves, emanating from the collision of two black holes over 1 billion light-years away. It was an auditory confirmation of his theory, a sound from a silent universe, arriving 100 years after he first wrote down the score. The decade of grueling intellectual labor had yielded a timeless masterpiece. Yet, even as the universe confirmed his masterpiece, the ground of physics was shifting once more, this time in a direction its chief architect found profoundly unsettling. The quantum revolution, a fire he himself had helped to light with his 1905 work on the photoelectric effect, was now raging with a strange and probabilistic logic. A new generation of physicists, led by figures like Niels Bohr and Werner Heisenberg, formulated the Copenhagen interpretation, which described a subatomic world governed by chance, uncertainty, and the act of observation itself. For Einstein, who saw in the universe an intelligible and deterministic order, this was an abdication of the physicist's highest calling. His famous declaration that God does play dice was a concise expression of a deep philosophical conviction that beneath the apparent randomness lay a deeper causal reality waiting to be uncovered. This conviction spurred him to become the new theory's most brilliant and persistent critic. Alongside his colleagues Boris Podolsky and Nathan Rosen, he constructed a masterful thought experiment in 1935, which became known as the EPR paradox. The paper, titled "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?", was a direct challenge to the foundations of the new physics. It imagined two particles, once linked, flying apart to opposite ends of the universe. According to quantum mechanics, measuring a property of one particle, like its spin, would instantaneously influence the corresponding property of the other, regardless of the distance separating them. Einstein derided this as spooky action at a distance, a violation of the principle of locality that underpins relativity. He believed this paradox demonstrated that quantum theory was offering an incomplete statistical snapshot, and that hidden variables must exist, local properties the particles carried with them, that predetermined the outcome of any measurement. For decades, his challenge remained a philosophical puzzle, a testament to his profound intuition. The decisive theoretical blow came in the 1960s from the physicist John Bell. Bell's theorem translated the philosophical debate into a mathematically testable proposition. Subsequent experiments, most definitively by Alain Aspect in the 1980s, confirmed the predictions of quantum mechanics with stunning accuracy. The universe does seem to permit this strange, non-local connection. Einstein's search for local hidden variables had reached a dead end. Still, the value of his descent was immense. His relentless, incisive questioning forced the proponents of quantum theory to clarify their positions, to grapple with the bizarre implications of entanglement, and to solidify the conceptual framework of their science. His skepticism, while ultimately steering him away from the mainstream, served as a crucial intellectual whetstone, sharpening the very theory he sought to undermine. His intellectual isolation grew more pronounced as he dedicated the final 3 decades of his life to a separate, all-consuming quest, the search for a unified field theory. Working from his office at the Institute for Advanced Study in Princeton, he sought the ultimate simplification, a single mathematical framework that could describe both gravity and electromagnetism as different manifestations of a single underlying field. This was the logical culmination of his life's work, an attempt to write the final chapter that began with relativity. He was pursuing the same aesthetic ideal of elegance and unity that had guided him to the field equations of gravity. He filled notebooks with complex tensor calculus, exploring geometric structures in higher dimensions, believing the secrets of the universe were encoded in a grand, harmonious equation. This monumental effort, however, yielded little fruit. While the rest of the physics community was busy exploring the rich and messy world of the newly discovered strong and weak nuclear forces, Einstein's work appeared increasingly detached from the frontiers of experimental science. The theories he produced were mathematically elegant, yet they made few testable predictions and failed to incorporate the growing particle zoo. He was, in a sense, trying to complete a puzzle with several crucial pieces still missing from the box. The grand synthesis he envisioned remained elusive until his death in 1955. His final scribbled equations were another step in this long, solitary journey toward a goal he would ever reach. To assess Einstein's legacy is to look beyond the ledger of successes and failures. His ultimate contribution resides in the very character of his thought. He was the supreme practitioner of the Gödel experiment, the thought experiment. From the very beginning, his mind was his laboratory. He probed the nature of reality by imagining what it would be like to ride alongside a beam of light, or to be a passenger in an elevator accelerating through empty space. This method, a form of structured intuition guided by deep physical principles and mathematical rigor, allowed him to ask questions that others had yet to formulate. It was a way of thinking that revealed the internal contradictions in classical physics and illuminated the path toward a new conception of the cosmos. This same intellectual engine powered his later critiques of quantum theory and his lonely search for unification. These endeavors, while producing few definitive answers, posed the most profound questions imaginable. His debate with Bohr was a deep inquiry into the nature of reality, causality, and measurement itself. His quest for a unified theory was a bold assertion that the fundamental forces of nature ought to be linked in a single coherent story. These were the grand challenges he bequeathed to future generations. Today, the central ambition of theoretical physics,
The pursuit of a theory of quantum gravity that would reconcile his general relativity with the quantum world is the direct intellectual heir to Einstein's final unfinished project. Albert Einstein, therefore, stands as a figure whose influence is measured as much by the territory he charted as by the destinations he reached. He provided a new grammar for physics, a new way to speak of space, time, matter, and light. He taught science how to dream again, using the power of pure reason to construct visions of the universe that were at once beautiful and true. The echoes of his solutions are all around us in the technologies we use and the cosmic wonders we observe. The echoes of his questions still resonate in the deepest corridors of our laboratories and in the minds of those who continue to gaze at the stars, seeking the final, elegant simplicity he so profoundly believed was there.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.